At the end of this lesson, the students will be able to understand about scope and excitement of physics, fundamental forces in nature, understand the concept of measurement, understand about significant figures, understand about accuracy and precision. Physics is one of the fundamental sciences. Physics is derived from the Greek word physis, which means nature. Physics expounds natural phenomena that we come across in our lives like the day and night, seasons, lightning, rainbows, etc. It deals with the study of a number of basic laws that governs nature. There is a rhythm and pattern between the phenomena of nature which is not apparent to the eye, but only to the eye of analysis, and it is these rhythm and patterns which we call the physical law. This famous phrase given by R.P. Feynman. The scope of physics is infinite. It studies phenomena that is microscopic as well as macroscopic. There are several branches of physics that tells us how diverse the subject of physics is. Physics is exciting because it is a subject that describes how the various things we come across in life are related. The theories of physics may be challenging to some, while experiments in physics may stimulate others. Modern technological gadgetry is mostly based on physics principles such as electricity, magnetism, heat, light, and sound, etc. Discoveries in the areas of physics herald more and more technological inventions. These new products create a need for new factories and provide employment to the people in the society. Thus, physics contributes to the economic development of countries. The influence of physics on related disciplines is great. Instruments based on physical concepts often provide the necessary infrastructure for other disciplines such as medicines, agriculture, IT, alternate energy, etc. Physics can provide the solutions for the general problems of the society. Physics enhances our knowledge of the Earth's environment. With the latest technology, we can manage rural disasters like earthquakes, hurricanes, etc. effectively. We can also conserve our environment by better understanding of global warming, causes of pollution, or ozone layer depletion. In nature, interactions exist between the tiny particles of matter as well as the huge objects in the universe. They are explained in physics by the four basic forces in nature: gravitational force, electromagnetic force, strong nuclear force, weak nuclear force. We experience gravitational force and electromagnetic force in everyday life. The strong and weak nuclear forces occur inside the nucleus of the atom. Formerly, the CGS, Hpbose, MKS system are used widely in different parts of the world. The most commonly used physical quantities, namely length, mass, and time, have the following unit in these systems. CGS system means centimeter, gram, and second. Hpbose system means foot, pound, and second. MKS system means meter, kilogram, and second. If we choose to measure as we wish, there would be a disorder as everyone's measurement would be different because of the different units used. Sizes or lengths in a range of few millimeters to hundreds of meters can be directly measured with a meter or a tape. In order to determine small sizes and lengths of the order of 10 to the power of -4, 10 to the power of -5, we use instruments like vernier calipers, screw gauge, and spherometer. Sizes or lengths beyond these ranges, like the size of a proton or distance between the Sun and the Earth, are determined by indirect methods. Measurement of large distances. Large distances such as the distance of a planet or a star from the Earth can be measured with a method known as the parallax method. When you hold a pencil against a specific point on the background, that is a wall, and look at the pencil first through your left eye, A, by closing the right eye, and then look at the pencil through your right eye, B, by closing the left eye, you would notice that the position of the pencil seems to change with respect of the point on the wall. This is called parallax. The distance between the 2 points of observation is called the basis. In the following example, the basis is the distance between the eyes. To measure the distance d of a faraway planet S by the parallax method, we observe it from 2 different positions, that is, observatories A and B on the Earth, separated by distance AB is equal to B at the same time as shown below. Now measure the angle between the 2 directions along which the planet is viewed at these 2 points. The angle ASB in the diagram, represented by symbol theta, is called the parallax angle or parallactic angle. As the planet is very far away, B by D is lesser than 1 and therefore theta is very small. Then approximately take AB as an arc of length B of a circle with center at S and the distance D as the radius AS is equal to BS, so that AB is equal to B is equal to d theta, where theta is in radians. D is equal to B divided by theta. Having determined d, a similar method can be used to determine the size or angular diameter of the planet. If d is the diameter of the planet and alpha the angular size of the planet, the angle subtended by d at the Earth, alpha, is equal to d divided by d. The angle alpha can be measured from the same location on the Earth. It is the angle between the 2 directions when 2 diametrically opposite points of the planet are viewed through the telescope. Estimation of very small distances. Size of a molecule. To measure a molecule, an optical microscope uses visible light to look at the system under investigation. As light has wave-like features, the resolution to which an optical microscope can be used is the wavelength of light. For visible light, in the range of wavelengths is from about 4000 angstrom to 7000 angstrom. 1 angstrom is equal to 10 to the power of -10 meters. Instead of visible light, an electron beam can be used. Electron beams can be focused by properly designed electric and magnetic fields. There is limited resolution of such an electron microscope. The wavelength of an electron can be as small as a fraction of an angstrom. Such electron microscopes with a resolution of 0.6 angstrom built. In recent times, tunneling microscope for estimating the sizes of molecules. A simple method for estimating the molecular size of oleic acid is given below. Oleic acid is a soapy liquid with a large molecular size of the order of 10 to the power of -9 meters. The idea is to first form monomolecular layer of oleic acid on water surface. Now dissolve 1 cm³ of oleic acid in alcohol to make a solution of 20 cm³. Then we take 1 cm³ of this solution and dilute it to 20 cm³ using alcohol. So, the concentration of the solution is equal to 1 divided by 20 into 20 cm³ of oleic acid per cm³ of solution. Next, lightly sprinkle some lycopodium powder on the surface of water in a large trough and put 1 drop of this solution in the water. The oleic acid drop spreads into a thin, large and roughly circular film of molecular thickness on water surface. Then we quickly measure the diameter of the thin film to get its area A. Suppose we have dropped n drops in the water. Initially, we determine the approximate volume of each drop, that is V cm³. Volume of n drops of solution is equal to nV centimeter cube. Amount of oleic acid in this solution is equal to nV into 1 divided by 20 into 20 centimeter cube. This solution of oleic acid spreads very fast on the surface of water and forms a very thin layer of thickness T. If this spreads to form a film of area A centimeter square, then the thickness of the film T is equal to volume of the film divided by area of the film, or NV divided by 20 into 20 area centimeter. If the volume has monomolecular thickness and then it becomes the size or diameter of a molecule of oleic acid, the value of thickness comes out to be the order of 10 to the power of minus 9 meter. Ranges of lengths. The sizes of the objects in the universe vary over a very wide range. The table below gives the range and order of lengths and sizes of some of these objects. Certain special length units can be used for short and large lengths. These are 1 Fermi is equal to 1 F is equal to 10 to the power of minus 15 meters. 1 angstrom is equal to 10 to the power minus 10 meters. 1 astronomical unit is equal to 1 AU. Average distance of the Sun from the Earth is equal to 1.496 into 10 to the power of 11 meters. 1 light year is equal to 1 LY is equal to 9.46 into 10 to the power 15 meters, that is distance that light travels with velocity of 3 into 10 to the power 8 meter per second in 1 year. 1 parasec is equal to 3.08 into 10 to the power 16 meter. Parasec is the distance at which average radius of Earth's orbit subtends an angle 1 arcsecond. Measurement of mass. Mass is a basic property of matter. It does not depend on the temperature, pressure, or location of the object in space. The SI unit of mass is kilogram, kg. The prototypes of the International Standard Kilogram supplied by the International Bureau of Weights and Measures BIPM are available in different countries. In India, this is available at the National Physical Laboratory NPL, New Delhi. An important standard unit of mass, called the Unified Atomic Mass Unit U, has been established for expressing the mass of atoms as 1 unified atomic mass unit is equal to 1 U is equal to 1 by 12 of the mass of an atom of carbon minus 12 isotope carbon with mass number 12 and atomic number 6 including the mass of electrons is equal to 1.66 into 10 to the power of 27 kilograms. Large masses in the universes like planets, stars, etc. based on Newton's law of gravitation can be measured by using gravitational method. Small masses of atomic or subatomic particles, etc. can be measured by mass spectrograph in which radius of trajectory is proportional to the mass of a charged particle moving in uniform electric and magnetic field. Range of masses. The masses of the objects vary over a wide range. These may vary from tiny mass of the order of 10 to the power of minus 30 kg of an electron to the huge mass of about 10 to the power 55 kilogram of the known universe. The table below gives the range and order of the typical masses of various objects. Measurement of time. To measure any time interval, a clock is needed. We now use an atomic standard of time, which is based on the periodic vibrations produced in cesium atom. In the cesium atomic clock, the second is taken as the time needed for 9,192,631,770 vibrations of the radiation corresponding to the transition between the two hyperfine levels of the ground state of cesium-133 atom. The vibrations of the cesium atom regulate the rate of this cesium atomic clock. The cesium atomic clocks are very accurate In principle, they provide portable standard. The national standard of time interval second as well as the frequency is maintained through 4 cesium atomic clocks. A cesium atomic clock is used in the National Physical Laboratory (NPL) New Delhi to maintain the Indian Standard of Time. The Indian Standard Time (IST) is linked to this set of atomic clocks. The efficient cesium atomic clocks are so accurate that they impart the uncertainty in time realization as plus or minus 1 into 10 to the power of minus 13, and that is 1 part in 10 to the power 13. This implies that the certainty gained over time by such a device is less than 1 part in 10 to the power 13. They lose or gain no more than 3 μs in 1 year. In view of the tremendous accuracy in time measurement, the SI unit of length has been expressed in terms of the path length light travels in certain intervals of time. 1 divided by 299, 792, 458 of a second. The table below gives the range and order of some typical time intervals. The ratio of the longest and shortest lengths of the objects in our universe is about 10 to the power 41. The ratio of the longest and shortest time intervals again in table, which lists typical masses of atoms. We measure a number of quantities in physics. We also face uncertainty in measurements. Error is nothing but this uncertainty in measurement. In other words, error is the difference between a true value and a measured value. The center of the target represents the true value. A measurement is said to be accurate if it is as close to real value as possible. If we choose to measure as we wish, there would be a disorder as everyone's measurement would be different because of the different units used. A measurement is said to be precise if the measurement lie within a small range. In either case, the measurement is approximate because of errors in measurement. 2 types of errors generally occur in measurements. They are systematic errors and random errors. Systematic errors. Systematic errors are consistent and they are introduced in all results. The effect of systematic error is to shift the measured quantity away from the actual value. A systematic error is one that always tends to be in the same direction, that is, positive or negative. Repeated measurements do not help in eliminating standard error because the problem is with the same instrument. Random errors. As the name indicates, random errors cannot be predicted. They may rise due to a number of reasons like voltage fluctuations, observer making an error while noting a reading, etc. They can be reduced by repeated measurements being taken. The least count error of instruments is an example of random error. Only those figures or digits of a numerical quantity that are obtained as the result of an actual measurement are said to be significant. For example, let us say the length of a pencil is measured and is found to be 14 centimeters. 23. The length can be written as 140 millimeters or 14 centimeters or 0.14 meters. Obviously, only the digits 1 and 4 are the actual measured values. Therefore, we have only 2 significant figures. Zeros used as placeholders are not significant. Scientific notation in powers of 10 is used to avoid ambiguity. Whenever scientific notation is used, remember that every digit that appears is significant. The power of 10 is immaterial in determining the significant figures. In scientific notation, we write the above measurement as 1.4 into 10 square millimeters or 1.4 into 10 to the power 1 centimeters or 1.4 into 10 to the power of minus 1 meters. The various measured values are displayed here.